Hey, this is Brock Lemires. We're continuing our study of embedded systems design. We are looking at the I2C peripheral on the MSP430. And in this video, we're going to finally take a look at the actual peripheral circuitry and configuration on the MSP430 FR2355, specifically implemented on the Launchpad board, because we are getting close to being able to write our first I2C program. Okay, so on the FR2355 version of the MSP430, you have two peripherals that provide I2C, and they are the B0 and B1. Okay, so recall that you had 4 serial peripherals total on this MCU. A0 and A1 could either be configured to be UART or SPI. B0 and B1 now can be configured to be SPI or I2C. So that's why you can have up to 2 I2C. SPI gets 4. You can have up to 4 SPIs, whatever. Okay, and up to 2 years. These are shared, just like all the other serial peripherals, with port pins. So if you look at B0, there's 2 lines always on an I2C bus, clock and data, SCL and SDA. And for B0, it is port 1, bit 3, and bit 2 for clock and data. Now those actually come out right here. It's pretty handy on these little pin header, or these pins right here on header J1. So if you want to grab your I2C lines for the B0, they're really accessible right there. B1 is also accessible. Its clock and data are on port 4, bit 7, and 6 respectively. And so those ones come out right here on the Launchpad board. So those are also easy to grab. As always, on an MCU, every pin on the package shares multiple functions. So in this table you see here, here's port 1, bit 3, port 1, bit 2. If you don't change the function select registers for these port bits, that's their default. But if you want to use I2C, you have to go into the port function select registers and flip them over into I2C. Same thing with port 4, bit 7, and 6. You got to flip them over into I2C. So just like we had to do with UART and SPI. Okay, so here it is. This is the system. Now I have redrawn this from the data sheet because there was a lot of stuff in the data sheet that it's a little overwhelming to begin with. But what we're going to do is we want to go through the main subsystems in here in order to get a feel for what's the bare minimum that needs to be set up in order to actually get a message to be sent. And there's more settings than in SPI and UART, I'm not gonna lie, but there's also so many settings in here that you don't want to learn every single one of them before you do your first program. Holy moly, here are all the configuration registers. Now, take a deep breath. There's a lot. You're going to have the control word, just like we've used before on UART and SPI. We have word 0 and word 1, and we actually have to set bits in both of them. You see some that you notice, though. You see your bit rate control word, that we're going to have the same kind of clock prescaler stat functionality. We got a status. We got some new ones, though. Byte counter. Not sure what that is yet. I mean, we'll get there in a few seconds. We do see a receive buffer and transmit buffer. I like that. I2C own address 0 through 3. That's kind of cool. That happens to be how you set up the slave address if you're going to be a slave. Receive address, or these are actually register addresses if you're a receive address. Receive address would be if you're a slave. Address mask, I2C slave address going out. And then, of course, your interrupt, enable, flag, and vector. So a whole lot of stuff here. Some of these are only used for slave mode. Some are used for master mode. And so we just kind of go through and find the settings that we need for a particular, task, the task at hand. Okay, just like the other peripherals, though, the way that you configure it is the same. You put it into software reset by setting the UC software reset bit in the control word 0 register. And then you initialize all your I2C configuration register settings. Then you configure the ports, and then you take it out of software reset, and then you enable the interrupts, which is optional, but we will always do that. So it's the same kind of settings that we had on the other peripherals. All right, so let's look at some of the key things that we have to do in order to get this thing to go. So first of all, look down here. This is the clock system. Now, we're going to look at master first. So we're always talking about being the master. As master, we generate the clock. Now notice that here's our open drain output stage. So you have the open drain output stage on the clock, and you have the open drain output stage on the data, and that's great. Down here on the clock, it's exactly like SPI. So you have the ability to choose your input clock that serves as your bitrate clock. You can choose from an external pin, or you can choose from A clock or SM clock. So same thing there. You also have the prescaler, so that's the BRW register, and again, you just drop in an integer value in here, and that tells you how much you're going to divide down your source clock. So, you know, if you want to get 100 kilohertz, you select a megahertz and divide by 10. Same thing. And now notice that the clock goes out to the outside world, and then it also serves as the clock for everything else in the system, like the shift register in and shift register out. Okay, a few other notable things. You know how when we initiate a message, one of the first things that the master sends out is a slave address. Well, it turns out that there's a slave address register that you put the address that you're trying to talk to in here, and then it's automatically taken care of for you. So a lot of the stuff that you're going to see is that we set it up, and then the state machine within the system itself actually builds the message and handles kind of the acknowledgement and back and forth. The read-write signal, that's configured in some settings we'll see it in the control word 0 register. But like I say, it's also automatically sent out at the right time. So once we start a message, which we will do manually, the slave address and the read-write bit will be automatically shifted out. And then what happens is the state machine automatically handles whether or what to do if there's an ACK or a NAC. And so this is built into the state machine. So it's counting the clock periods and handling this for us. Depending on whether you're reading or writing, if you are writing, then you have this transmit buffer. That's where you put your information that will be shifted out when appropriate. So if you're going to write, you know, you send the start bit out, you send the slave bit out, you send the write bit out, and then whatever's in transmit buffer will be shifted out. And watch the path here. It goes through the open drain output stage, and then it comes up and it goes out the pin, and life is good. When you are reading, what happens is that notice that this pin right here is also connected to the input shift register. So what happens is that you send the start bit, you send the slave address, you send the read bit, and then when it's shifted in, it will arrive in the receive buffer. And so that's kind of how the in and out works. There's something that's really cool about this system is it's got a register called a byte counter. And so the byte counter is how you tell the system how many bytes of data will be sent or read within a message. So if you're only going to write a single register, not provide a register address or anything like that, and you just want a byte, you just want to do slave address and then write a byte, or slave address and read a byte, you set the byte counter to 1, and that's how many will be pumped out. And so this counter holds an integer value. So if you put 8 in here, the state machine is going to attempt to write 8 bytes of data. So it'll write a byte, wait for an ACK. Write the second byte, wait for an ACK. Write the third byte, wait for an ACK. Same thing when receiving. It'll read it, ACK. Read byte 2, ACK. Read byte 3, ACK. Read byte 4, ACK. It's very useful, as we'll see, because it marks the end of the message, and it can be used to trigger an automatic stop bit. Okay, so now let's look at the two, I would say the two primary configuration registers. These are going to be control register 0 and control register 1. We've been using control register 0 for SPI and UART, and remember, on B0 and B1, this is the same register name as when you set up the system in SPI. It's just that the bit fields change. And I highlighted these in gray for which ones are different, whether you're in SPI or I2C mode. So you can see, you go through here, we're going to start at bit 0 and walk down. You can see its own addressing mode. Is it 7 or 10 bits? Slave addressing mode, 7 or 10 bits. We're always going to work with the default, which is 7 bits, because that's the most common. Multi-master environment, how do you handle that? I'm not going to look at that. Here's a couple settings that are a bare minimum needed to get this thing working. Number one, if UC mode, you got to put it into I2C mode. Remember, you have SPI mode takes up 3 of these settings. I2C is really just, it's the last one. So if you put 1 into UC mode right here, it's going to say, oh, I'm in I2C mode. And then you got to tell it, are you a master or are you a slave? Because whether you're a master or a slave, there's a pretty significant difference in how you set this up. So I'm a master here. That's what I want to do, what I'm looking at right now. So I would have to set that bit to be the master. If we look at the rest of the bits, since we're a master, we absolutely have to set the clock. So we're going to do that up here in UC SSEL to choose which clock we're going to use. Note that, of course, we're going to have to go set the baud rate control register to set the prescaler, which is a separate register, but this is where we do the clock select. This right here is the read or write. So this tells you whether you're going to transmit or receive, and you can change this message by message because you might be doing back-to-back messages to access a register, and you need to write the register address and then read from that register. So it's perfectly acceptable to change this during the program, just not during the message. You've got some settings for like automatically doing how to handle like a knack, automatically transmit a stop. So all sorts of interesting things. This bit right here is very interesting because this is how you start a message. So if you write a 1 to this bit right here, this UCTXSTT, that starts the message. And so you get everything set up, and then what we do is when we're ready, we set this bit and it begins the message. This automatically generates the start bit. It automatically shifts out whatever's in the slave address register. It automatically sends out the bit that is in the read write or transmit receiver, this UCTR, and then it waits for an ACK, and then after the ACK, it responds accordingly. If you're writing, it'll take whatever is in the TX buffer and shift it out. If you're receiving, it'll count bits until you get the information in and then put it in the receive buffer. So this is the little guy right here that we're going to use. Over in the control word register 1, now this is the first time we've used the other configuration register. There's a real key setting here. There's some, there's a whole bunch of stuff in here that's for like strange situation. I'm abnormal, I guess. They're beyond bare minimum, like a clock low time select and stuff like that. This bit right here is really cool. Automatic stop condition generation. So if we go to these bits right here, we can tell this to work in conjunction with the byte counter. And this is how we're going to do everything. This is what I found is the easiest way. So if we come in here and do 10 on these bits, these UC STP, if you do stop generated automatically after a byte counter reaches value in the TB count register, this is what we want. And then what we do then is we just set up the byte counter for how many bytes that we want to send. And then if we set this up correctly, after the byte counter has sent that number of bits, we don't have to do anything for the stop bit. The stop bit is automatically generated. And so I've found that this is the easiest thing. So we will be setting this single bit in the control word 1 register. As always, you've got interrupts, and holy cow, look at all the interrupts. We've got 15 different interrupts you can use with this, and this is just like overwhelming when you look at it. But like I say, you just kind of only use the ones that you need at the time and kind of read through and figure out if one is going to meet your needs. So look at all those interrupts. Of course, all of them have their own flag. And then, of course, you have your interrupt vector, which is just a prioritization scheme. So if you did have multiple interrupts, you can use this to tell which one has the highest priority. Again, we're not going to use this. We're going to only be doing like one or two interrupts at any given time. So we don't really need to use that. But here's what we'll kind of wrap up with. There are 2 interrupts that are essential when you're reading and writing. One is the transmit interrupt and one's the receive interrupt. So the transmit interrupt, this is how you interact with the system. So what happens is that after a message is started, it's going to shift out the slave address. Okay. Then it's going to shift out the read write bit. Then it's going to wait for an ACK. If there's an ACK, this thing, and you're writing, this thing fires. And then what the interrupt service routine does is say, hey, there's somebody out there that's ready for data. You need to put information in the transmit buffer. So this indicates when data can be written to the transmit buffer, and it only fires when you had a successful ACK from a slave. So this is how we actually write information. And then the other big one that you have to use is the read buffer. So when you are going to do a read, what happens is that it's going to do the start bit, then it's going to shift out the slave address and then the read bit, and then information is going to come shifting in. And 8 clock cycles later, information will be in and will be shifted in. It is then put in the receive buffer, and then you need to go get it. So this will fire and trigger an interrupt service routine that you will then go and grab the information out of the receive buffer. Notice, just like every other one of these, this is only one interrupt vector. So you have to share a functionality within one interrupt service routine for that vector. Okay, that is it. So now we are getting very, very close to being able to write our first program. There's just a couple more things that we need to look at, but that is an overview of the master operation on the MSP430 FR2355. As always, support my channel by subscribing, and see ya.